Welcome to Lecture 16, the final lecture on this course on rheology. In this lecture, we're going to look at emulsions, which is a dispersion of two immiscible liquids. They look at first sight quite similar to suspensions, but there's one key and important difference. Droplets of an immiscible liquid can deform under the action of shear or extension. And as these droplets change shape, the rheological response of the system also changes in a way that we don't see in suspensions. So, in this part of Lecture 16, we're going to introduce ourselves to an emulsion and to some very elegant and informative results that allow us to predict the shape and orientation of droplets within shear fields. So, let's start by examining a cartoon of an emulsion. So here we go. An emulsion consists of droplets of an immiscible liquid in a surrounding liquid. Imagine oil in water, for example. If the two liquids are at rest, these immiscible droplets are spherical. Surface tension causes them to minimise the surface area, so they become spherical. Now, if we place these droplets in a shear field, and I've written a shear field there in tensor form for you on the board, the shear field will elongate them and also rotate them. Interestingly, the maximum angle of rotation that can be obtained is 45 degrees relative to the direction of flow. So, in a shear field, droplets rotate and elongate. In extensional fields, and I've again written an example of an extensional deformation, a uniaxial deformation, there as a reminder on the board in tensor form. In extensional fields, droplets don't rotate because there's no rotation associated with extensional flows, but they do elongate. So, under the action of deformation, the discrete phase of an emulsion can rotate or elongate. We're going to focus on shear fields, and we're going to introduce a very important definition that applies to both shear and extension. Imagine a spherical droplet. Under the action of a deformation, viscous forces are placed on this droplet. Imagine that tau equals eta gamma dot. Gamma dot is our rate of deformation. Eta is the viscosity of the continuous phase. So the continuous phase exerts a viscous stress on the dispersed phase and causes it to change shape. And our initially spherical droplet becomes ellipsoidal. Now, imagine that we stop that deformation. Surface tension takes over. Imagine surface tension, if you will, as a great big rubber band around our droplet. It forces it back to be spherical again. It minimises its surface area and it restores the original droplet shape. You could imagine that if the surrounding liquid is highly viscous, there may be some time taken for this shape restoration to occur. So maybe that should trigger the thought of emulsions might be thixotropic. Right, so viscous forces and surface forces. The interplay between these two forces is so important that we define a non-dimensional group to describe it, the capillary number. Viscous forces divided by surface forces. Capillary number there I've written on the board is r, the droplet radius, or a measure of radius, eta gamma dot over sigma. Sigma here is surface tension. The surface forces is sigma over r. The viscous forces are eta gamma dot. So we're going to use capillary number a lot in the description of deformation that follows. Here on the board, I've put a cartoon of a shear field. The white lines with arrows are streamlines of a shear flow. The blue background is our continuous liquid phase with a viscosity eta continuous. Within this continuous liquid phase, I'm going to place a droplet. This droplet rotates and deforms with the shear flow and becomes an ellipsoid. This ellipsoid has a semi-major axis length B and a semi-minor axis length C. There is also a viscosity associated with this ellipsoid, eta disperse. Now, a few quantities I'm going to put on the board now. We need a measure of shape because we're looking at deformation. So ellipticity is B minus C over B plus C. If B equals C, i.e. our droplet is spherical, ES is 0. As our spherical droplet elongates into an ellipsoid, ES increases. Kappa is a viscosity ratio, the ratio of the dispersed phase to the continuous phase. And also there on the board is that all-important non-dimensional group, the capillary number, viscous stress over surface stress. So, there's a very elegant paper that was published in the Journal of Fluid Mechanics in 1968 by R.G. Cox. The full reference is in your lecture notes. And this is a completely first principles fluid mechanics approach to describing how droplets deform in various deformation fields. He looks at both their dynamics and their asymptotic steady state response. We're only going to examine the asymptotic steady state results, but they tell us some very important physical properties of emulsions. One important result describes the ellipticity as a function of capillary number and viscosity ratio. So there is the result on the board. This is a very, very lengthy derivation that we certainly don't have the opportunity to explore in this course. Also, he describes how the droplets rotate. Now, the important thing to remember when looking at the rotation results is the axis of rotation is defined to be from a direction perpendicular to the flow direction. I've drawn theta there on the board between our semi-major axis B and that perpendicular direction to the direction of flow, which is very important to remember, otherwise you get a very unphysical picture of what the rotation actually is. So that rotation theta is also a function of viscosity ratio kappa and capillary number. So those are the two expressions we're going to examine. Let's first of all examine some limiting cases. One limiting case we can look at is if the capillary number tends to 0. If the capillary number tends to 0, that means that surface forces dominate. Surface tension effectively dominates. So we would imagine that under dominant surface tension, our droplets remain spherical. And ES does indeed tend to 0, indicating a spherical droplet. Theta, our orientation axis, tends to 45 degrees. But if our droplets are spherical, we can't actually see that rotation anyway. Another limit we can examine is what happens if the viscosity ratio tends to infinity. Now, kappa tending to infinity means my disperse phase viscosity is highly greater than my continuous phase viscosity. And if we think in analogue what a very high disperse phase viscosity looks like, we're approaching suspension behaviour. The discrete entity is more and more solid-like, i.e. non-deformable. So again, my ellipticity ES is the result that is spherical. It tends to 0. My orientation angle is 90 degrees, but again, because we've got a spherical droplet, we can't actually see that visually. What we will do now is plot these two equations out on a graph so we can see the full range of behaviour that droplets have in shear flows. So here on the board now are some sets of axes. This primary y-axis is my ellipticity, my droplet shape. And remember that if E subscript S equals 0, I have spherical particles. And for E subscript S greater than 0, I have ellipsoids. So I've put a visual reminder there for you on the primary y-axis. My secondary y-axis is the orientation direction. Remember, this is with respect to the perpendicular direction of the flow, not the flow direction itself. The x-axis is viscosity ratio, the disperse phase viscosity over the continuous phase viscosity, and remember, as kappa tends to a very high number, the droplets start to behave like particles because that disperse phase viscosity gets very, very, very high. So let's look at a few cases. Now, for a low capillary number, let's say 100th, so low capillary numbers are where surface tension dominates. What we see in terms of droplet shape is very little deviation from spherical. So at low viscosity ratios, where I have an easily deformable droplet, I get a tiny, minuscule deviation away from the spherical result. And with increasing viscosity ratio, we get the spherical result, i.e. approximately 0. If we look at the orientation of these spherical droplets, we can see that at low viscosity ratio, deformable droplets, easily deformable droplets, we have an orientation 45 degrees. and with increasing viscosity ratio an orientation of 90 degrees. But we've got a spherical droplet, so we can't really see that experimentally. So that's with a low capillary number where surface forces dominate. Let's increase our capillary number a bit. Let's go from 1/100th to 1/10th. So the dotted lines on the blackboard now are for capillary number 0.1. If we look at the shape there plotted in dark blue, we can see that we have a little bit of droplet deformation for viscosity ratios where droplets are easily deformable. For viscosity ratios where droplets are not easily deformable, they maintain their spherical shape because they're effectively behaving as solid particles. If we look at the orientation for low viscosity ratios, where we see slightly ellipsoidal droplets, we will see that they will be orientated at 45 degrees from the flow direction. As we increase the viscosity ratio, those ellipsoidal particles tend to spherical, and we will see that we get that result where they're aligned with the flow direction again, or 90 degrees perpendicular to the flow direction. Now, let's increase the capillary number some more. Let's go to 0.9. Now we start to see significant droplet deformation. If we look at those ellipticity values, they're as high as 0.9 for easily deformable droplets. And in that regime of easily deformable droplets, we will see that these droplets are oriented 45 degrees to the flow direction. As we increase that viscosity ratio, again what we see are the ellipsoids tending back to spherical droplets, and their orientation going more and more and more aligned with the flow direction, or 90 degrees to the axis that is perpendicular to the flow direction. So there is a visual summary of droplet behaviour in shear flows. Let's recap a few key points. We're starting to look at emulsions, which are mixtures of two immiscible liquid phases. A key non-dimensional group that governs the behaviour of emulsions is the capillary number, viscous stress over surface stress. As capillary number tends to 0 in an emulsion, we see that we have spherical droplets. Surface tension dominates, forcing minimisation of surface area, i.e. a spherical entity. As capillary numbers tend to 1, we've seen that we have ellipsoidal droplets at viscosity ratios where the droplets are easily deformable, i.e. the droplets have a low viscosity relative to the continuous phase. We've seen that both the deformation extent, the ellipticity, and the orientation angle depend on the viscosity ratio kappa and on the capillary number.